All right, so here we're going to be going over some projectile motion examples. I'm going to go over a few FRQs just to keep the video length reasonable. And so we're going to cover a horizontally launched projectile, a projectile on level ground, and then we're going to deal with a projectile when it's not level ground. And, these are going to be very helpful examples for the upcoming test. So the very first one is pretty straightforward. We have horizontally launched projectile. We've seen this many times, and everyone did pretty well on the quiz, so I'm not too worried about this. So here we have, here's an example. So say we have some books stacked up here, and it's 0.5 meters off the ground, okay, and we're going to launch a projectile off the table, and it's going to land on the books, all right? So the path of a projectile is in the shape of a parabola, and basically we got to sort of figure out the horizontal range and the vertical height that it falls. So let's actually do that. So here the vertical height, y. Well, we know the table is going to be 2 meters off the ground, right? So the height of the table is going to be 2 meters. That's where the projectile is launched. And we know that it's going to land on the books, which are 0.5 meters off the ground. So basically, being able to reason that the distance that the projectile actually falls is going to be 1.5 meters. All right. Now, in terms of the velocity, let's say that the initial velocity, let me make up a number here. Let's say it's 3 meters per second. Okay, so 3 meters per second, that is the velocity in the x direction, and it's a horizontally launched projectile. Right, so horizontally launched projectile. All right. So some things that we can find the amount of time it takes for the projectile to actually fall. And then based on its horizontal velocity, we can use the amount of time that it's falling in order to figure out the horizontal range, right? So this is going to be the horizontal range of the projectile. Now, the way that you want to figure out the amount of time that it falls, so there is a shortcut, right, that we can use. So if we know that the vertical velocity starts off at 0, then we can use something that's called the free fall equation. And this little shortcut, you can just use the square root of 2y over g, where y is the amount of distance that it falls. And if you want to understand where that comes from, we need to go over the full equation, right? So the full equation that we have is one of the kinematic relations. So we know the equation of motion is this, x equals v naught t plus 1/2 at squared. I'm just going to relabel it so that we understand we're dealing with the y direction. So y is equal to v naught y times t plus 1/2 a sub y t squared. Okay. Hold on, let me see if I can. Okay, I'm going to turn this off. There we go. Okay, so anyways, so where does this free fall equation come from, right? Because it's not necessarily on the equation sheet. But it's just a useful shortcut when you know that v naught y is 0. If you look at the equation over here, if I set v naught y equal to 0, right, and then I just have y is equal to 1/2 a sub y times t squared. Well, I know that the acceleration in the y direction is going to be 9.8 going down, right? So I can just replace that with g, okay? And that's basically where the equation comes from. If you want to do the algebra to solve for t, we'll just go over it to be thorough. So I multiply both sides by 2, and then I divide both sides by g. All right, so then I have 2y over g equals t squared. And then finally, I take the square root of both sides, right? So square root of 2y over g is equal to t. All right, so that's where the free fall equation comes from. You can really just use this for horizontally launched projectiles, or if you just drop a ball, right, and you see the amount of time it takes to fall a certain distance. In both cases, the vertical velocity is going to start off at 0, so you can just use the free fall equation. So let's calculate it. We know it's going to fall 1.5 meters, all right? So let me get to my calculator, and I have, so 2 times 1.5, we get 3, obviously, and divide that by 9.8. Okay, 0.306. Now you can take the square root of the answer. What I personally like to do is I just raise it to the 0.5 power, right? Because if you raise a number to the 1/2 power, that's the same thing as taking a square root, right? So that just saves a little bit of time. So here we get 0.553 seconds, all right? So let's go back to here, and we get that t, here I'll just write it out. So 2 times 1.5 meters over 9.8 meters per second squared. All right, I'm just leaving everything positive because I understand this projectile is falling down, just going into downward direction, and that's the same direction which is accelerating, right? The acceleration due to gravity. So here we do the math, and we just saw that it was 0.553 seconds. All right, so t is equal to 0.553 seconds, and I'll underline that for now to get the actual horizontal range. So here, for the horizontal range, I know that the velocity in the x direction, so velocity in the x direction is constant. And the reason why the velocity in the x direction is constant is basically there's no acceleration in the x direction. When you're in free fall, the only force acting upon you is the force of gravity, and that's pointing downward. So if I were to draw a free body diagram on this object, I know that the only force acting on it is the force of gravity, and it's pointing straight down. So there's not going to be any forces in the x direction. The acceleration is 0, the velocity is constant. So here for the range, right, since the velocity is constant, we know that v is going to equal x over t. And if I rearrange that, I get that x is equal to v times t, but specifically v sub x, right? So the horizontal velocity is what's constant, and that's what we get for the range when you're dealing with a horizontally launched projectile. So let's actually just go through the math. We have 3 meters per second for the velocity. For the time, we calculated 0.553 seconds. Okay, and let's just multiply those together. So that's our time in seconds. I don't know why it's showing that again. So I'm just going to take that answer, and I'm going to multiply that by 3. And I get 1.66. Okay, so 1.66 meters per second. All right, so that's it. That's the answer for that one. Now let's look at an example where we're dealing with a projectile that's launched at an angle. All right, so here I have some projectile. Let me just draw a line to kind of separate the two problems. So here I have a projectile that's traveling with some initial velocity v naught. It's at an angle of 45 degrees, and we know that it takes 2 seconds to reach its max height. All right, something that's very important to know about projectile motion is at the very top. All right, so let me put this in a different color. So this is something that you just need to know. So at the very top, at top of parabola, the vertical velocity is 0. Right, so I'll write that as v, not v not y, but the velocity in the y direction is going to be 0 when you're at the very top. And I've mentioned this many times, but the reasoning is very simple. On the way up, its vertical velocity is going to be going upward, right, in the positive direction. On the way down, the vertical velocity is going to be going downward, right? So we can say that's in the negative direction. And 0 is in between a positive and negative number. At the very top is when it transitions from going up to going down. So that's kind of the logic behind that. So some questions that we can ask is, well, what's the vertical velocity, right? So we're kind of working backwards in this one, where the initial velocity is not given, but we need to figure out what the vertical velocity is. The way that you can find that, so just to clarify, we are asking, say we did part A, what is the initial vertical velocity? The initial vertical velocity of the projectile. Okay, so what is v naught y? Well, in order to figure that out, we know that it took 2 seconds to reach the very top, right? So this is going to be, accelerating at a rate of 9.8, right? That's the gravity on Earth. So we can very easily figure that out. So I'm just going to go over the kinematic relation. So we know the final velocity is 0 when it reaches the top. The initial velocity is what we're trying to solve for. And we know the acceleration, and we obviously know the time. So the kinematic equation that we're going to use is this one. This is basically the definition of acceleration, but it's just rearranged to solve for the velocity at some point in time. So we know that let me rewrite this using y, right? So we understand that we're dealing with the y direction. So plus the acceleration in the y direction times t. And now let's plug in some values, right? So we know that the vertical velocity at the very top is going to be 0 meters per second. That's going to equal the initial vertical velocity, which we don't know. And we know that the acceleration due to gravity, I'm going to call going up positive and going down negative for this example. Ultimately, it doesn't matter. As long as you're consistent, you're going to get the same answer. So here I have negative 9.8 meters per second squared. And then the time is going to be 2 seconds. And let's just calculate that. So what I'm going to do is, I know that 9.8 times 2 is negative 19.6, right? So that's how much my velocity changes, 19.6 meters per second. And then I'm just going to move that over to the other side of the equation, right? Because I have 0 over here on the left-hand side. So I know that the initial velocity in the y direction is 19.6 meters per second for this example, okay? So part B, let's say we need to figure out what the horizontal velocity is, right? So here I have a 45-degree angle. All right, and we need to figure out what that vertical horizontal velocity is. Okay, so the logic behind that is, oh, actually, hold on a second. Well, we know the horizontal velocity is going to be the same because it's a 45-degree angle, right? So we have our x component and our y component, right? So v naught y. And we have v sub x. The velocity in the x direction is not going to change. Only the y direction changes. But I believe a better example is figuring out what the actual initial velocity is, right? So part B is going to be what is the initial velocity of projectile. All right. And just to clarify, this is the actual initial velocity, right? So that's the vector sum, right? So vector sum of x and y components. Right. So the way to think about this one, we know that the y component is going to be equal to v naught times the sine of 45. The reason that it's the sine of 45 is because, well, we know that the v naught y here is going to be the opposite side. V naught is the hypotenuse, right? So the sine is the function that we're going to want to use because sine of theta is equal to opposite over hypotenuse, right? So I'm just going to write that out. I know that the sine of 45 degrees is going to equal the opposite side, which is v naught y, and the hypotenuse is v naught. And since we're solving for v naught, when you do the math, you're going to see that v naught is going to equal v naught y divided by the sine of 45 degrees. Right, so let's just plug in the values. I got 19.6 meters per second. I'm going to divide that by the sine of 45, and we're going to need to bust out the calculator. All right, so 19.6 divided by the sine of 45 degrees, and we get about 23. All right, so 23.0. All right, so I get 23.0 meters per second. All right. Here, let me make sure I got that right. Yes. Okay. Yeah, so 23 meters per second. So, wait, hold on a second. That seems a bit off. I knew it. Oh no, you gotta be careful. You've got to be careful. See, that's what I get. I installed this app on my iPad and I didn't check whether or not I was in degrees. All right. So how did I know that was a little bit off? Well, I know that sine of 45 is about root 2 over 2, which is like 0.7. And if I divide it by 0.7, that seemed kind of low, the 23. All right. So, you know, as you keep doing math problems, you're going to kind of get a feel for numbers. And this is a perfect example of why we got to be careful. You got to check your calculator, make sure you're in degrees. All right. So I know in math class, you got to do radians a lot of the times, but here in physics, we have to be in degrees. I'm actually kind of happy that happened, just to make sure that your calculator is in degree mode when you're performing the calculations. All right. So now let's do it for real. 19.6 divided by the sine of 45 degrees, not 45 radians. 45 degrees. Oh, wait, what am I doing? I multiplied them. Whoops. All right. Divided by the sine of 45 degrees. There we go. All right. So 27.7. That is the official answer. All right. 27.7 meters per second. There we go. Perfect. So that is going to be, this is an example of just, you know, projectile motion when it's launched at an angle. You have to worry about that initial velocity in the y direction, and you're going to use just the kinematic relations, just like we've always been doing. Now, how do we deal with a projectile that is not at level ground, right? So recently we did a lab where we used the books so that the marble launcher actually doesn't really change in terms of height. Now, if it does change in terms of height, there are ways to work with that. There's a general range equation where you have to solve using the quadratic equation, but we don't have to deal with that in this problem. All you need to do is the same process as with level ground. You need to calculate the amount of time. No, actually, typically what you need to do is you calculate the amount of time that's going to be in the air by looking at the x direction, and then from that, you can figure out what the vertical position is going to be. So let's work through this problem. This is part of the review. This is going to be very relevant for the test. So we have a human cannonball shot at 45 degrees. All right, so let me set that up. Hold on a second. Oh, wait. How do I get rid of this? Yeah, there we go. Okay, so here we have, so here's the cannon. All right, and this person, this is a human cannonball, so he's going to get shot out of the cannon. And we're going to say that he gets shot out. His initial velocity is going to be at 45 degrees, V naught. And we know that V naught is equal to 25 meters per second. So 25 meters per second. And then there's going to be a net positioned at a horizontal distance of 50 meters. All right, so here, let me draw my net. Wait, I'm not sure if I'm going to have enough space for this. 1 second. Yeah, I should be fine. So here we have our net. And we need to figure out what the vertical position of the net is going to be. So what is this vertical position of the net? So one thing that we can do is we can figure out the amount of time that's in the air. So we know what the horizontal range is, and we can figure out what the velocity in the x direction is. All right, and then from that, we can get the horizontal range. So the horizontal range remains the same, right? So that is just the horizontal velocity times time. So if we need to solve for time, I'm going to divide the horizontal range by the horizontal velocity. Now we need to get what the actual velocity is, right? So again, we're going to find the components. This time we're going to use cosine though. So if I have a 25 meter per second vector at an angle of 45 degrees, right? So this is the angle of 45 degrees. I know that the y component is going to be equal to 25 times the sine of 45, right? Because that's the opposite side, and the hypotenuse is 25. So yeah, sine 45 degrees, okay? And the x component, right, is going to be cosine, because the x component here, that's the adjacent side to the angle. Hypotenuse is 25. So to solve for the adjacent side, we know it's going to equal 25 times the cosine of 45. All right, so let's get these values. What we're going to see is, hold on, let me get to the calculator. Wait a minute. There we go. All right, so now, let's see, we got 25 times the sine of 45. Well, that's going to be the vertical component. And we know that it's going to be the same for cosine, because cosine 45 is the same as sine 45. So here we get 17.7, right? So let's round that to 17.7 meters per second. All right, and from that we can figure out how long it's going to be in the air. So I know that I have a horizontal range of 50 meters. Is traveling, his horizontal velocity is 17.7 meters per second. And then from that, we can calculate the time. Let's get the calculator out. So I'm just going to do 50 divided by the answer, right? We can do, wait, where's the, oh, there it is. Okay, so 2.83. That's how long it's going to take. So t is equal to 2.83 seconds. Okay, so now the height that the cannonball, or I'm sorry, the height that the net needs to be off the ground. So this is when you have to look at the y direction, right? So the kinematic relation is going to be y is equal to v naught y times t plus 1/2 a sub y times t squared. And in terms of like where we got that from, it's just like this example over here, right? The equation on the equation sheet is going to show x, right? But x just represents the displacement. If you want to write it in terms of y, you just write y. That's the vertical displacement, right? So it's the same exact equation. I'm just using slightly different symbols to signal that it's in the y direction. So here we have, we're trying to solve for y. So we're trying to solve what position does the net have to be to catch the human cannonball with a given initial vertical velocity. We know the acceleration due to gravity is 9.8. More importantly, we have t. So we figured out t by looking at the horizontal range. We know he's going to be in the air for 2.83 seconds. So you just got to plug in the values. All right, so we saw that the vertical velocity is 17.7 meters per second times t squared. Oh, I'm sorry, times t, 2.83 plus 1/2 of gravity. So if the initial vertical velocity is positive, right, implicitly we're saying that up is positive, that would mean that down is negative. All right, so you have to put negative 9.8 meters per second squared times, well, t squared. All right, and let's plug this into the calculator. So that's my time. Actually, I'm just going to store this as a variable. All right, so let me just store that as t. So I'm just showing you little calculator tricks to kind of make your work a little bit easier. So here I have my time variable t, and I'm just going to start going through all the calculations. So I have here 17.7 times t. Okay, I don't even need to put it in parentheses. And then we're going to add negative, or I should say, hold on, did I put the 1/2? Yeah, so I put the 1/2 there. Okay, so 1/2 Whoops. Oh, I guess I never entered it. All right. Anyways, 17.7 times t plus 0.5 times negative 9.8. Wait a second. I got to put negative. No, there we go. Negative 9.8 times t squared. All right. So here we get 10.86 meters. Okay. So let's go to here. You put all that in the calculator. 10.86. Let's see how many sig figs we got. So we got 3 sig figs. So it's going to round to 10.9 meters. All right. So that's our final answer. That is going to be the vertical position of the human cannonball after he travels 50 meters, right? So after 50 meters, it takes him 2.83 seconds to travel 50 meters because we looked at the horizontal velocity, we calculated the time. And then, well, if he's in the air for 2.83 seconds, what's going to be his vertical displacement after 2.83 seconds? You use the equation of motion, and we found his vertical displacement is going to be 10.9. So yeah, that's where you should put the net. If you want to catch the guy, you want to put it where his vertical position is going to be. So here, let's check and make sure we got it. And yeah, it says 10.8. But anyways, based on our calculations, we round up 10.9. All right, that's what it should be. But yeah, basically we got it. So that's good. And that's really the only types of questions that you need to see. So we covered, as a recap, we did horizontally launched projectile, right? That one's pretty straightforward. We did a projectile at level ground. And then we finished off with a projectile where it doesn't land on the ground, right? So it lands at, some different vertical position, but that's not that much more complicated, right? All you need to do is solve for t. Once you have t, you plug it into the equation of motion, and that's about it. All right. So anyways, I hope that was helpful. If you have any questions before we get to the test, you can always email me, and I'll be more than happy to help. The reviews are going to be useful. Again, you don't have to complete every single review problem, right? It's just there for your benefit. Like, I think there's a bunch of multiple choice, but it's going to tell you whether or not you get it correct or incorrect. Just do as much as you can. The more problems that you do, the more that you figure out, the more comfortable you're going to feel with the content. But at the minimum, you need to make sure that you know how to do these problems, okay? So that's